A very good afternoon to all the students. So in today's session we are going to discuss one important topic regarding this advanced encryption standard, that is AES Key Expansion. Right. So as we know that if you consider the AES algorithm with 10 rounds, how many subkeys are required? So how many subkeys are required for a AES with 10 rounds?
Forty-four, sir.
44, right. The generalized formula is n plus 1, where n is the number of rounds and it is 10 plus 1, and therefore it is 11 subkeys are required, and each subkey is a 4-word subkey. So totally we have 44 words of keys are required for the AES with 128. Right. So in this session we are going to discuss, but what is the input that we are giving? What is the size of the input key size?
4 words, sir.
4 words. It is 128-bit cipher key, or else we can also call it as 16-byte cipher key, or else we can also call it as 4-word. Right. So what is the first key that we are going to give it to the first round, that is preliminary round? So we consider it as K0. And what are the words we have? W0, W1, W2 and W3. Am I right or not? So this is pre-round. This is the key for pre-round. What about the key for first round? I call it as K1. So what are the words? We should start with W4 followed by W5 followed by W6 and then W7. And this is for round 1. What about round 2? I take it as K2 and I call them as W8, W9, W10 and W11. This is for round 2. Like that you need to use different keys K1, K2, K3 and so on up to K10 for different rounds. Right. So what is the last round key? We call it as the round key for the last round, that is round 10 is K10, where we get it as W40, W41, W42 and W43. This is for round 10. Is it clear up to this point?
Yes, sir. Yes, sir.
So the input to the AES algorithm is this one only. What externally we are providing as a user, as an end user, what externally we are providing the key is the key which is given to the pre-round. Right. This is what we are providing. That means we are going to provide only 4 words of cipher key, and we need to convert these 4 rounds of cipher key into 44 words of cipher key. Therefore we call this, we are expanding the key from 4 words to 44 words. Therefore we call this technique as the key expansion method, which is used in AES algorithm. Right. So how this W4, W5, W6 and W7 are generated, this is our topic of interest at the present session. Right. How we are going to generate W4, how we are going to generate W5, W6, W7. So if we know how to generate the subkey for one round from the previous round, then the practice or the steps has to be repeated for generation of other keys from the previous keys, right? So you should understand one point here is that the keys or the words of the keys of one round are dependent on the words of the keys of its previous round. So the round 1 key is dependent on pre-round. Similarly, the round 2 key is dependent on round 1. Round 3 key is dependent on round 2. So the round 10 is dependent on round 9. This is very important that you should understand, right? Is it clear up to this point? The simple point is the key that we are going to use for each and every round in AES is dependent on its previous key. Clear?
Yes, sir.
Yes, sir.
So how can I represent the key? What is the representation that we are using for key? What is this representation called?
Rows and columns.
Rows and columns only, but it is called as an array, right? So the key is always represented as a 4 by 4 array. So in the representation topic which we have discussed in the earlier sessions, I have clearly mentioned that the input is a 4 by 4 matrix. Similarly, the output is a 4 by 4 matrix, and the state array is a 4 by 4 matrix. Similarly, the key is also a 4 by 4 matrix. And what is the size of the key? What is the size of the key?
48 bits, sir.
48 bit is in DES, right? But I am asking about AES. What is the size of the key? Avinash, please mute yourself. So, what is the size of the key we have in AES? It is 128 bit, right? So what is the size of the key? It is 128 bits, right? So 128 bits are 16 bytes or 4 words. So the first byte is given here, second byte, third byte, fourth byte, and fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14, 15th byte and 16th byte. So this is how we are going to represent it, right? So what is word 0? Word 0 corresponds to the first series of bytes here, and word 1 represents the second colon, this one, and the third word represents the third colon, and here we have W3, right? Is it clear up to this point?
Yes, sir.
This is K0, right? which is B0, B1, B2, B3, B4 and so on up to B15. So I represent this B0 to B15 in this array, 4 by 4 array. Now you have to generate the second key, K1. So what is K1? It is W4, W5, W6 and W7. Am I right or not? Now we need to generate this W4, W5, W6 and W7 from the previous round key, that is from W0, W1, W2 and W3. So first of all, let us calculate how do we find this W4, that is the first word of key 1. So the formula for finding out the first word of key 1, that is W4, is given by W0 exclusive or Z of W3. This is very important formula, very simple formula, right? So in order to generate W4 of that is the first word of key K1, I am going to use W0 and W3, right? So this is important to generate key and this is important. So what is that we are using to generate W4? We are using word 0 and word 3 of K0. Is it clear?
Yes, sir.
So it is just an exclusive OR of W0 with W3, but this W3 has to be given as an input to a function. G is nothing but a function. That's it. Now we will see what this function is. Right. So before knowing what this function is, actually we should know some of the important steps that are required for generating or creating a word from the other words, right? So this we will see now. You just keep this particular topic in mind, that W4 is generated with exclusive OR operation of W0 and some function G on W3, right? Now we will see the steps that are required, steps for key expansion, very important. This is how the key expansion algorithm works. The first step in the key expansion, we call it as the rot word. Rot word is nothing a new term, it is nothing but the rotation of a word. Simple term. Rot stands for rotation. And the second step, after rotation, you have to perform the substitution operation. And after performing the substitution, we need to perform the round const, right? Round constant. We can call it as round constant. We'll see what each and every one is, right? So these are the three steps that are very important for calculating the words of a key from the previous keys. So we have three steps. The first one is rotation, second one is substitution, and the third one is round constant. Substitution means you are all very well aware of this particular term, right? So substitution is always performed with the help of which box?
S box, sir.
S box, right? So let us see what happens in step 1. Very simple steps, right? So what is step 1? It is nothing but rot word. So in this rot word, what you have to do is you have to consider W3, right? Let us draw the diagram here so that it will be clear for you. So this is W0, this is W1, W2 and W3, and this is B0, B1, B2, B3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. So what is that I have to take? In the rotation word, I have to take only W3. Only W3. And you arrange this W3 in the vertical fashion. It's not vertical, horizontal fashion. Right. Like this you have to arrange. And now you have to perform the rotation. The rotation is nothing but rotation towards left. That's it. Towards left. Right. And one important point I have already keep on telling you, that when you are operating things by making use of left shift or right shift, you should specify how many bits you want to shift or how many bytes you want to shift. Here the rotation is the left rotation by 1 byte. Clear? Is it clear up to this point? So when you rotate this particular word W3 1 byte left, what is that output I will get here? So this will move here, B13, this will move here, and this will move here, and B12 will go here. So the resultant will be B13 followed by B14 followed by B15, and then I have B12. Simple technique. Clear? Is it clear up to this point?
Yes, sir.
Yes, sir.
So if I take an example here, let us take W12, that means sorry, B12. B12 as some 54, B13 as some FE, B14 as AC, B15 as 23. Let us take like this. So these are the bits W3. These 4, B12, B3, B14 and B15. These constitute word 3 of K0. I have to arrange it in this order: 54, FE, AC followed by 23. So after left shifting 1 byte left shift, what you have to do? What is the resultant you will get here? If you left shift 1 byte of this particular word, what is that resultant I will get here?
FE.
Super. FE followed by AC followed
23,
by 23 followed by
54, sir.
54. Very simple operation, right? Now after this we have to perform step 2. What is step 2?
Substitution operation.
Substitution makes use of which box? S box. And as you know that this S box is a 16 by 16 matrix. And whatever you have, for example, if a cell is having FE, right, the first 4 bits represents, is it row number or column number? Rows. And the second 4 bits represents columns. This is what we have seen in the previous discussions also. The same concept we are going to apply here also, right? So what is that output we got from the previous step?
FE, AC,
So this is
23,
FE, AC,
23,
23,
54.
54. Super, right? So we have to substitute these bytes with the SBox values. So if I take the first byte FE, so what is the column I have to take? It is a 16 by 16 S by 16 by 16 matrix. I have to take the F row, this one, and I have to take the eth column. So wherever I get a value coincidence, that I have to take it, and I have to substitute this FE with this value, right? Similarly, you have to go for the second byte, and A is taken as the row and C is taken as the column. So you take 8th row and 6th column. Whatever coincidence you will get, you have to take that value, and you have to replace that AC with that value. Similarly, 2 3. In 2 3, 2 represents the row and 3 represents the column. So second row, third column, the corresponding value has to be taken. Here 5th row, 4th column. So 5th row, 4th column, the corresponding value has to be replaced with this particular the 54 has to be replaced with this corresponding value. So is it clear up to this point?
Yes, sir.
So after substitution, let us assume that FE is substituted with 1B. This is just an assumption. We have to go for the actual SBox and you have to find the values. But right now I am just taking an example, right? And assume that AC has to be replaced with 79. 23 is replaced with FF. 54 is replaced with 18. Let us take like that. This is 1B, or let us take it as 1A. Nothing wrong in it. So what is the output word I will get after substitution? FE is replaced with 1A.
Sir.
AC is replaced with 79. 23 is replaced with FF. 54 is replaced with 18. So this is the output of the second step. Clear up to this point?
Yes,
Clear?
sir.
Right. So we'll go for step 3. What is step 3 here?
Round constants.
Round constant, right? So we have to find the XOR operation of the resultant of the second step with the round constant, right? Round constant is again a constant matrix, right? Is again a constant matrix. Let us tell you what this round constant and how this round constant looks like. How many rounds are there in AES? Ten rounds, right?
Yes, sir.
So the round constant matrix is a 4 by 10 matrix. We can take it as a 4 by 10 matrix. Actually this is not a matrix, but round 1 looks like this: 0 1, all zeros. And round 2 is a constant value. The first value is 2 and then we have all zeros. And similarly round 3 is 4 followed by 4 zeros. Round 4 is 8 followed by 4 zeros. And then it is 10, 20, 40, 80, 1B, and finally I have 36. Remaining things are zeros. So this is a constant that is already defined by the developers. we don't have to worry about how this constant has been taken, why this has been taken. The thing is that we should concentrate on what operation we have to perform, right? So in the round constant step, you have to perform an XOR operation of, we have to perform an XOR operation of the output of second step is XORed with round constant, right? So what is the output we got from the second step? What is the output we got from the second step?
1A
1A
79
79 FF
18, sir.
18, right? So we are in round 1. So what is that column I have to take? I have to take this word only, right? So I have to perform an XOR operation 79 FF and 18. So what is the round constant for first round? It is 0 1 followed by all zeros. Am I right or not? I have to perform the XOR operation, right? So this remains as it is. So this will change. So the resultant will be the, what is this value? What is that I have used here? This is the transformations, the resultant of the transformations that is applied on W3. Am I right or not? What is the first thing I have taken here? What is that I have taken here? It is W3. On W3 I have applied the root word, and then from the result I have applied the substitution, and from the output I have applied the XOR operation of round constant. So the final result is from W3. Do you accept it or not? Right? It is the resultant of the output which I get from W3. So what is 1A and 0 1? What 1A exclusive or 0 1? How can I perform this operation? Any idea? So this 1A is a hexadecimal notation, right? So 1 should be represented with 4 bits. What is the value here? 0 0 0 1. What is A? What is A? 10, right? So you should represent it as 1 0 1 0, and here this is 0 0 0 0, and this is 0 0 0 1. So I have to perform the XOR operation of this 1A with 0 1. So what is that I will get? This is 1, this is 1 0 1 1, and XOR operation means whenever we have same bits we will get the output as 0. Whenever we have different bits we get the output as 1. So what is that I will get here? This again convert it into hexadecimal. This is 1. What is the value here? What is the value? 1 0 1 1 means 8 plus 2 plus 1, that is 11. So how do you represent 11 in hexadecimal notation?
We're now on
B, sir. B, sir.
B, right? So here I will get it as 1B. So the entire word which I have generated here is the result of some operations on W3, right? So what is the formula that I have given for W4? W4 is given by W0 XOR of G of W3. Am I right or not? I told that this G is a function. So how can I write this function? It is W0 exclusive OR. What is that I have performed on this W3? What is the first step I have performed? What is the first step I have performed?
Rotation.
Rot word of W3. And after that, what is that I have performed?
Substitution.
Substitution, sir.
Substitute. And after that, what I have performed?
Round constant, sir.
Round constant. So this G is nothing but it is defined as round constant of substitute of rot word. So G of W3 is nothing but round constant of substitute of rot word of W3. Is it clear up to this point?
Yes, sir.
Right. So what is W0
Yes,
here?
sir.
What is W0? So this one, right? B0, B1, B2 and B3. Right. It is B0, B1, B2 and B3. This is W0. Exclusive OR with, what is that resultant I got in the previous one? It is 1B followed by, can you please tell me?
79.
79 FF, am I right or not?
18.
FF
Yes. 18.
18,
sir.
right? Now you have to perform the exclusive OR operation of this B0. I am not taking the values of this one, right? B0 with 1B, that is, here you can write like this. You can take some example and you can explain. That's not an issue. FF and 18. You have to perform the exclusive OR operation. So whatever result you get, that is equivalent to W4. So this is the step you have to follow. Now W5. What is W5? Can anybody tell me what is W5? K0 is the key for the preliminary round and K1 is represented with W4, W5, W6 and W7. So we have generated one word from K1 by using this particular functionality. W0 exclusive OR round constant of substitute of rot word of W3. And W5 you have to generate. That means the second word of the key1, key K1, right? So W5 is given by formula W1 exclusive OR W4. It's a simple thing. So you take the original W1, so this is W0, W1, W2 and W3. To generate W4, I have used W3 with some function and W0. To generate W5, I have to use W1 exclusive OR with W4, which is generated here. Similarly, the third word of key K1, W6, is generated by using the formula W2 exclusive OR W5. And the last word W7 is generated by the word W3 plus W6. Clear? Is it clear up to this point? So I have generated the 4 words of key K1. Now, what is that key K2? What are the words I have? W8, W9, W10 and W11. So can anybody give me the formula of W8? How can I generate W8? What is W8?
W4 plus W6.
right, it is, sorry, just give me 1 minute. So what is W8? It is W4 exclusive ARD with function G of the last word, that is W7. So what is G here? It is again the same. It is the round constant of substitute of root word of W7. That's it. Now what is W9?
W5 XOR of W8.
W5 exclusive R with W8. What is W10? W6 exclusive R W9. What is W11? It is W7 exclusive R W10. Right. Like that you have to generate every key for each and every round. Is it clear? How many steps are involved in the key expansion?
3, sir.
What are they? Root word,
Word, substitution operation, round constant, sir.
round constant, right? So now tell me, for generating this W4, W5 and W6 and W7, I have to use the round constant R1, which is the 0 1 followed by 4 zeros. And what about the round constant for generating this one? W8, W9, W10 and W11. I have to use the second round constant, which is 2 0 0 0 0 0 0. Right? For round 4, I have to take the fourth round. Round 4 means, what are the values I have for round 4?
0, 8, sir.
Right, this is 0 8 0 0 0 0 0 0. So you have to take this constant. So this is how we expand the key from 4 words to 44 words. Is it clear?
Yes, sir.
So we'll quickly go through the slides. So if you are able to understand what I have told till now, it will be very easy for this one. So coming to AES expansion, to create round keys for each round, AES uses key expansion process. If the number of rounds is NR, the key expansion routine creates NR plus 1, 128-bit round keys from one single 128-bit cipher key. Right, we are having only 128-bit, which is represented as W0 through W3, and we need to generate 44 words from this 4 words. This is what the key expansion is. So as I told that the pre-round makes use of the original cipher key, that is W0, W1, W2 and W3, and round 1 makes use of W4, W5, W6 and W7. Like that NR makes use of W4NR, W4NR plus 1, 4NR plus 2 and like that, right? So how we are going to generate the T4, T's and something like that, right? So if you observe this one, look at this last one, blue colored. It's a simple formula, right? So in order to get the word of 1 TI, what I am doing here, I am taking WI minus 1, right? So if I want to get W4, what is that I am taking here? WI minus 1, that is W3 I have to take. And what is that I have to apply here? First one is root word I have to apply. Second, the output of the root word is given to substitute word. Now we are substituting. After substitution, I take the R constant, that is round constant, and I perform the exclusive OR operation, right? So this is how I generate the key. Clear? right? So the round constant is exclusive OR with the output of subword or substitute word to get the final one. Clear?
Yes, sir.
So this is T4, but in order to get W4, what I have to do? This is T4, right? So whatever result I get here, that should be XORed with W0. Therefore, that is the reason why I am writing it as W4 is equal to W0 plus G of W3. So this G is nothing but this one, this entire thing, right? And W5 is given as W1 exclusive OR W4. W6 is given as exclusive OR of W5 and W2. W7 is given as exclusive OR of W6 and W3. Clear? This is what we have explained up to this point. And these are R constants. R constants, as you can see that this is a hexadecimal value 0 1 followed by 4 zeros. This is for round 1. For round 2, 0 2 followed by 4 zeros. Round 3, 4 followed by 4 zeros. Round 4, 8 followed by 4 zeros. 5, 10, 20, 40, 80, 1B and 36. So these are for 10 rounds. Sir, what is the procedure for AES 192? The same procedure applies, but the number of rounds may vary. That's it, right? Maybe the size of the key which you are taking may also vary, right? So this is for 12 round. And remaining things, AES 256 means it is for 14 rounds, right? The same procedure has to be applied. So this is the explanation or the algorithm what the author has given for the key expansion in AES 128, right? So here is an example of one particular word that is taken, key that is taken, and how it is going to be applied. That is what he told, right? So you can see that this is a 16-bit, that is 16 byte key that was taken. Alice and Bob are the characters that are taken here. Alice is the sender and Bob is the receiver. And this is the key that has been given. So this 4 bytes is equal to W0. And these 4 bytes W1. And from here to here it is W2. Here to here it is W3. Right? So you take the first round W0, and in order to generate this W4, you have to calculate the T, which is nothing but the function G of W03, this one. Finally, you exclusive OR this result with this one to get this one. And this is how the key is generated for all the 10 rounds. Clear?
Yes, sir.
Yes, sir.
So each round key in AES depends on previous round key. This is what I told in the first point. So the dependency, however, is non-linear because of subword transformation, right? So it is non-linear. That means if you change one bit, it is not going to change only those many bits. It is a non-linear. If you change one bit of cipher key, it is going to change the entire text, because this is only possible because of this subword transformation, substitute, right? S box. So the addition of round constants also guarantees that each round key will be different from the previous one. And the two sets of round keys can be created from two cipher keys that are different only in one bit. See here. See here I am taking the cipher key K1 and here I am taking the cipher key K2. Both are same only, right, except for this one bit, right? A and B differ by only one bit. It's not byte, right? So only one bit have changed, but look at what happens if you take the actual thing, right? Right. So if you take the first cipher key, this one, which is having AA, this is AA and this is AB. So in the preliminary round there is only one bit difference. BD stands for bit difference, only one bit difference. And in the second round I have 2 bits of difference. That means this is for K1, this is K0. And for the second round, see here how many bits are difference I have, K2. And in the third round, K3 is having 30 bits, K4 is having 31 bits, K5, K6, and this is K7, and this is K8, this is K9, and this is K10. So at the end of this K10, see here 52 bits have been changed, but originally the cipher bit, how many bits are having difference with the initial key, that is the cipher key? Only 1 bit. But at each and every round it is going to generate different bits differences depending upon. This is possible only because of S boxes and the round constants, right? Clear?
Yes, sir.
And the concept of weak keys, which we have discussed in the DES, doesn't have any importance in AES. Why? Because weak keys make the algorithm vulnerable to the attackers. But here, even though you take weak keys like this one, all zeros is a weak key, right? But still the AES algorithm is able to generate very good ciphertext at the end of 10th round. This is the strength of AES. But in DES, if you have weak key, after 2 rounds you are able to generate the plain text again. That is the only disadvantage we have. But if you take the weak keys in AES and you apply it to the AES algorithm, at the end of round 10 you are able to generate a very strong ciphertext. This is the strength, right? So if you observe, the words in the pre-round and the first round are all same. See here, this word is same, this is same, this is same, this is same. Similarly in the second round, 6263, 6363, all these words are same, right? Keys, these are keys. And in the first word matches with the third. Here if you observe that this matches, first word matches with the third word and second word matches with the fourth word. And from the, however, after the second round the pattern disappears. There is no sequence of patterns that appears equally, right? Every word is different from every other word. So this is the strength of AES. Even it will work for the weak keys, even it will work for the semi weak keys, even it will work for possibly weak keys. All these things we have discussed in DES, right? Clear?
Yes, sir.
Right. So as I told that the key expansion algorithm in AES 192 and AES 256 is almost similar as the key expansion algorithm in AES 128 with some key differences, right? So here we are going to use, it is going to compute 6 new rounds for AES 192 or 8 new rounds for AES 256 of the subkey array W, right? And the subkey for the first AES round is formed by the array of elements, this one, and the second subkey is found by this one, and so on. This point we have already discussed, right? Clear?
Yes, sir.
Simple thing you have to remember is that the key expansion algorithm remains same for AES 192, AES 256 and AES 128 with very minor differences with the number of iterations it is going to take to generate the subkeys. That's it, right? And coming to the last topic, the key expansion analysis. The key expansion mechanism in AES has been designed to provide several features that resist. Thwart means resist the cryptanalyst. So no cryptanalyst, no sophisticated cryptanalyst can attack the key the AES algorithm with respect to the keys, right? Is it clear? Is the okay, right? So in today's session we have gone through the key expansion process that is taking place in the AES algorithm. The key expansion technique makes use of it is used to generate the next key from the given cipher key, right? And you have to remember that the key of one round is dependent on the key of the previous round. Like that, we have some formulas, right? In every key generation, we need to follow, if we need to take a function which is a combination of 3 steps, that is the rotation word followed by substitution followed by round constant. All these 3 steps I have explained with an example, and the other words like W5, W6 and W7 can be calculated with the recently generated word, that is W4, whereas W4 is given by W0 plus, that is exclusive or G of W3, where G stands for rot word of substitute of round constant, right? You should remember what this round constant is. For each and every round we have different words of constants, and you need to apply the round constant as the last step of the word generation, right? And after that, we have seen how these weak keys have no effect on the strength of AES. Even though you take a weak key like all zeros, it is going to generate different keys for different rounds, right? So this is all about the key expansion in AES, and this is end of today's session. Thank you one and all for joining the session.